Hello, my name is Georg Kohl, and in this video I'm going to talk to you about how we can learn similarity metrics for numerical simulation methods. I've been working on this together with Kivon and Niels Thuray here at the Technical University of Munich. First, a quick overview over the motivation and the main task we're trying to solve. Essentially, we are interested in similarity assessment of 2D simulation data from partial differential equations, or PDEs. You can see a few example sequences down here. The main goal is to bring these sequences into a sensible ordering that you can see on the right. The simplest idea of just looking at the data and arranging it accordingly does not really work in all cases. The first few examples, it might work, but for a more complex case, for example, the third one we have here, the visual complexity is too high and it's not really possible anymore. Instead, one could use an L2 or an L1 distance to compute distances between the simulation frames and then order them accordingly. But the main issue with that is that structures and patterns are entirely ignored by these metrics because they only operate on a single pixel-wise basis. Instead, we propose to use convolutional neural networks because they can recognize these spatial contexts and are much more suitable for a similarity evaluation. Also, a metric has to follow certain mathematical properties, which we will consider here as well. Down here, you can see another sequence example, this time a velocity field from a smoke simulation. And you recognize that the ordering on the right can also be expressed as a set of distances between the individual frames. So distances that are frames that are really similar get a small distance of 0.1, frames that are less similar 0.2, and so on until we have every possible pair labeled. So how can we create a model that predicts these distances for us? The first building block is a numerical simulation. So essentially, a numerical simulation uses a set of initial conditions and transforms it into an output via a PDE solver. Here we are interested in a sequence of data, so we have to change a single initial condition, in this case pi, in increasing steps, denoted by delta I here, to get the data sequence shown in the middle. These initial conditions also define our ground truth distances, where a higher change in the initial condition means the ground truth distance is going to be higher as well. The next building block is learning. First, we have to split up our data sequence into every possible pair that can be processed by our model. Our model in yellow here uses shared weights, so a Siamese architecture, and consists of two feature extractors, denoted with CNN here, that extract features from our two inputs. These features are then normalized and can be compared in the latent space to form our distance prediction of the network. Of course, this network is not perfect right from the start, so we have to introduce some optimization, and this happens via a loss between the ground truth distances and the predicted distance by our network that is then used, for example, by an Adam optimizer to change the weights of our network. The final block is the evaluation to determine if a metric that was learned actually produces sensible results. This is done via the Spearman's ranking correlation that takes the ground truth distance and the learned distance and computes the linear dependency between those. So a higher value means the learned distances represent the ground truth more accurately. A quick overview of our results. On the left here, you can see a single example comparison. In the middle, there's the reference plume and two variants A and B on the left and on the right. And visually, and also from the ground truth, plume A looks more similar to the reference. Our metric recognizes this fairly well, and you can see it here in the distance plot that the distance matches with the ground truth. For an L2 distance, the opposite is true, so it extracts distances in a way that are not really suitable, as you can see. Also, on our combined test data, a correlation evaluation shows that we're consistently achieving higher correlation values compared to shallow distances like L2, a structural similarity, or even like learned image-based distances, for example, LPIPs. This also brings us to the related works. There are three main categories of metrics that are applicable for simulation data. First, we have vector space metrics. We can also denote these as shallow metrics because they are not CNN-based. And these include the LP norms, as discussed before, a peak signal-to-noise ratio, or the structural similarity index. Furthermore, we can evaluate simulation data via user studies, so by essentially showing the data to a bunch of humans to determine the similarity. This has been done, for example, by OMED coworkers for liquid simulations and non-oscillatory discretization schemes. As you can imagine, this evaluation is quite costly and also takes a lot of time and is not really suitable overall. The third category are learned image-based metrics using CNNs. There are quite a few of them. Here is just listed, for example, LPIPs. And they are not really optimal either, because the data distribution of images is really different from the ones that we are interested in. Now a more closer look to the data generation. We start with a time-dependent motion-based PDE that you can see here in the center that computes different time steps via a solver. The solver is initialized with certain initial conditions P and produces an output O. We can then vary a single initial condition, Pi, in incremental steps, denoted by delta I here, to get multiple runs of the same simulation where a single thing changed so that the outputs are going to change in the same way. This means a smaller change in the simulation input results also in a smaller change in the output and also the other way around. This is not enough yet, because with this approach, the resulting data would be too simple. So an L2 distance would already be quite reasonable to assess the similarity. And as a result, our model would essentially learn this, but it's not really optimal. So we also introduce a noise that is differentiated for every time step of our solver. And the variance of the noise controls the difficulty of the resulting data. So a higher noise variance means the data is more difficult and the network is going to learn better. But of course, only until a certain point, because then the data essentially just becomes noise and the network is not able to extract any useful information anymore. With this approach, we created a variety of training data. For example, a grid-based smoke plume you can see on the top left here, with a density field, pressure field, and a velocity field. In this case, the varied initial conditions were, for example, the position and orientation of a downwards directed force field, the size and position of our source, or the direction of the buoyancy experienced by the smoke plume. On the top right, you can see our liquid data set computed via fluid implicit particles that consists of a breaking dam where a liquid blob is dropped into the pool. You can see the flag field at the top that corresponds to the area where liquid is and where there isn't. In the middle, you can see the level set. And at the very bottom, you can see the velocity of the liquid simulation. In this case, the position of the and size of the drop were varied, and also the direction of the gravity. Finally, at the bottom, you can see two one-dimensional PDEs, the advection diffusion transport and the Burgers equation, that are in this case stacked over time to form the 2D outputs you can see here. In this case, we used multiple layered sine functions to initialize the forcing terms, and they can be varied individually. For our test data, we used another liquid simulation, but this time we added noise to the background of the simulation. Second, we have the advection diffusion transport again, but this time we added the noise to the density field instead of the velocity field, resulting in a quite different data distribution. For the remaining test sets, we used a different approach to generate the data. Essentially, these are just temporal frames of a longer sequence, for example, in the shape data of moving shapes in linear lines. And for the video data, just a simple video that changes over time. The goal of the network here is to infer the correct ordering of the frames in time. Finally, we have the TID 2013 dataset that consists of simple images that are distorted with various distortions like added noise, compression, or a color quantization, as you can see at the bottom here. So how can we learn a model that actually computes these distances for us? As mentioned before, we start with a Siamese architecture, so shared weights, that consists of several convolution plus redo layers. The goal of the space network is to extract several features from the inputs, for example, edges or corners or certain shapes, that can then be processed later on. It is possible to use a vision-based network here, for example, AlexNet or VGG, but as they are using a different data distribution, we found that training a specialized model for this purpose works a lot better. So down here, you can see from the inputs, we get two sets of third-order tensors as the feature maps. The next step is normalizing these feature maps because right now they have a very different magnitude and cannot be compared equally. One idea would be to stack these features into a long vector and perform a unit length normalization on this. This results in a cosine distance, so essentially just an angle comparison where any kind of length is lost. Instead, we propose to use the entire training set and compute the distributions of every feature map that can then be used via the mean and the standard deviation to transform every feature map to a standard normal distribution. This results in a reasonable length for every feature vector, but the angle can be compared as well, meaning that we have more information than just a simple unit length normalization to compare later on. The core of the metric is the latent space difference, where we are actually comparing these sets of third-order tensors to form a single set of third-order tensors in this case. We found that this operation has to be a metric with respect to the latent space, meaning that we can, for example, choose an L1 distance or an L2 distance in this case here. We also tried more intricate functions where certain operations are learned, but we found that this works best. Finally, we have to compress these difference maps into a single scalar result. This is performed by the following operations shown in green here. And the first operation is a channel aggregation, meaning we have a single learned weight for every feature map and perform a weighted average to compress the features along a channel dimension. For the spatial and the layer aggregation, we're using simple sums and averages to compress the differences down to a single scalar value. To train this network, we are comparing the ground truth distances C and the predicted distance D. Our loss term consists of two parts, a mean squared error on the left that just minimizes the distance deviation of both distributions directly. And this is very important in the beginning of the training, where the distances have a quite different magnitude, meaning it has to be pulled towards the correct values first. Then we have the second term, and this is an inverted correlation term that maximizes the linear distance relationship between both distributions, and is mainly important for the end of the training, where the order of the different predictions is shuffled around. With our metric, we can achieve quite good results, as you can see here in this table. These are the Spearman's correlation values that we mentioned before of ground truth against predicted distances, where a higher value is better. The green values in the table are the best metric, and the red values are the worst. As you can see, shallow metrics like L1, L2, or the structural similarity don't really work well on most of our data sets. A learned image-based model performs really well on the TID data and the video data that is fairly similar to the training distribution that LPIPS was experiencing. But you can see that for a very different data distribution of numerical simulations that we have, our model consistently outperforms the others. To come back to the initial data, we have had a look at three different real-world data repositories consisting of transport flows that are captured via a multiple view reconstruction. This is the scalar flow data set on the top left. Then we have measured atmospheric quantities, for example, temperature or geopotential on the top right from WeatherBench, and turbulence velocities computed via direct numerical simulation or DNS from the Johns Hopkins turbulence database at the bottom here. In this case, the goal of the model always was to infer a spatial or temporal ordering in which the frames were created. For these data sets, we had 6 different interval spacing for every data repository with about 200 sequences each. In the diagram on the right, you can see the mean and standard deviation of the averaged Spearman correlations over the different interval spacings. You can see that our metric on the far right outperforms the 3 other models by consistently having a higher mean and a lower standard deviation. In the future, our learned metric opens up the possibility to quite few interesting research directions. First, we can more accurately assess the similarity of new simulation methods to determine their performance, or also parameter reconstructions or generative models of physical systems can benefit from an improved comparison. Furthermore, we would like to extend our data to 3 dimensions and also further PDEs. Finally, we would also like to introduce a multi-channel version, for example, for the velocity turbulence data that we saw in the end. So that's going to be it for me, and thank you very much for your attention. If you're interested in this topic and want to learn more, you can join our 2 live sessions that are coming up soon for more questions and the discussion. If you want to try out the model for yourself, you can find our source code here at the GitHub repository. Thanks for watching.